So in the class number 25th, in the last week, I showed you the derivations of the Mindlin plate bending, which is the thick plate. Well, of course, the thick plate will be applicable to the thin plate problem as well, because it incorporates all the deformations possible from both the bending and the shear mode. So we can use this for all situations for the plate. But as I mentioned last time at the very beginning of the class, that the use of the thick element like this, you should have the basic understanding. The derivations of the plate or the beam bending of these are under the bending assumption. So the plane sections remain plane is there. The mechanism of the force resistance is the bending mechanism. So you shall not oversimplify the problem, mechanics problem, using this plate bending or the beam bending. If the mechanism is not likely to be the bending or governed by flexures, for example, in the case where you expect the strut and tie mechanism like that, use the 3D continuum element. That's gonna be better than using the bending element. Alright, so hopefully you are going to use all of this in the right way. So that's what I emphasized last time, and now we come to this point here is the rigidity, the strain displacement relationships for the bending mode, and the size of the B matrix here is a little bit different from the size of B matrix we had for the plane problem, because here we have 3 degrees of freedom at each nodal point. So when you have 3 DOF at the nodal point, you need to spare the space in the B matrix. You need to spare the column for each cell for the node, for a given nodal point. Okay, make it 3 instead of 2. That previously you have just the U and the V for each node. Now you have the W, which is the vertical displacement or the vertical deflection and rotations in the followings. So you have in total 3 DOF. You need 3 columns, and basically in the bending mode, it has nothing to do with the first column, which is associated with the W. The vertical deflections is not a part for these formulations. It will be used later in the shear part, but you can see that it is very simple, because it is very simple now because you have come across the plane problem already. So in the plane problem, you have derivative of shape function with respect to global coordinates, right? So you have partial derivative of phi, whichever phi I, right, with respect to the x and with respect to the y directions. So we used to expand these terms into partial derivative of phi with x. Well, as the phi is actually formulated in the numerical domain using the c and eta coordinates, right? So you take the partial derivative of phi with respect to c and partial derivative of c with respect to x from the chain rule, plus partial derivative of phi with respect to eta and partial derivative of eta with respect to the x. Okay, that is according to the chain rule. We have seen the detail of that thing already, so we will not cover it for another time. So partial derivative is easy. We have the subroutine which was made already for the which is made to to perform all the calculations for these. So the matter of fact is that we can just take the codes for the plane problem and do some modifications in order to get it into the shape of the plate bending problem for the Mindlin's plane. So I'm gonna switch you back to the desktop screen, to the editor page. Okay, so now I think the size is big enough, I guess. The code we are going to use is the main. Let me get the iPad out of my way. It is obstructing my workplace. Now, file name, and I think the plate thickness wouldn't supposed to be here. Let me just cut it out and put it somewhere there, like XY coordinate before nmap, or maybe element type, or where number of integration point. I think I can put it here. Plate thickness is gonna be there. If the plate thickness is gonna be after the element type, direct match after element type. Okay, right. Okay, and ELE E type, and then we put the plate thickness. So, and why is the next thing the number of node? It is XY core. Huh? Why is it the number? Where is it? File name. So this is the printout. XY core. Well, let me call this one first then. Leg match to see the data structure a little bit before we move. Output to element type, make it 4 and X, 5 and Y, 5 HX, 2 HY, 2 file name, PLATE plate 1.text, and then check it in Octave page, plate 1. So plate element type, number of nodes, and then the read input read is going to get number of node, number of element, and XY coordinates. Okay, right. Then number of node, number of element type. Okay, so the rect match here, well, I kind of, so it wrote the file name info element type, number of nodes. It wrote it that way. And the number of nodes. Okay, so I just insert this. It's just gonna insert this after the element type. So make it the plate thickness. This is going to be the rect match for the plate, and I'm gonna just get the dot somewhere. Okay, here. So plate thickness, and then I just put the dot in, and that's it. Okay, save it, and call it again. Yeah, go ahead. Yeah, so we're gonna put the plate thickness over here. Element type is there, number of node, number of element, degree of freedom, elastic property or element properties. Okay, we put elastic modulus and Poisson ratio here, copy and paste, right? Number of integration points, we're gonna put in reduce integration. We're gonna do the no for now. Number of essential variation, okay, and then the load. Fine, looks good. And then the input read has to be total number of node, number of element. Before we go to the XY coordinates, we need to read the plate thickness. And yeah, the plate thickness. The matter of fact is that we gotta need to be consistent with all the parts of the function. PTHK plate thickness is the string to num. So the plate thickness is going to be after this, right? PTHK comma after the element type. Okay, make sure that you're gonna get all of this in the same way as in here. So element type, and then p thick, and here is the p thick we have. Okay, so input read should work. Main update, I adjust that, so we will only, and I should rename it Mindlin plate. Okay, of course the name of this has to be changed. Fine. We come down here, initializing the Gauss point, etc. We actually came all the way to this point. Last time we went through all of these, the DMAT for the shear and DMAT for the bending. This is the ratio of 5/6, which is the shear correction factor multiplied by the plate thickness multiplied by the dummy, which is that elastic modulus divided by the 2 times 1 plus Poisson ratio, which is the shear modulus. Right, that is from the notes. Okay, so DMAT S is there. Well, it's just one number. DMAT B is the rigidity matrix, and K ELI has to be 2 times element type because you have 3 DOF for each. Okay, E X Y C. Element XY coordinate is not going to be changed from before, so this is maintained. The loop integration point, this is all the same, but the BMAT turns out to be 3 rows by 3 times element type columns, whereas the BMAT S for the shear, you have just 2 shear strain. So 2 shear strains, you have just 2 rows, and this for each cell or for each nodal point you have 3 DOF, and then you have in total the number of column is 3 times the element type. Okay, and then you come next to the construction of the B matrix, and it is carried out like cell by cell. So you have 8 nodes. This operation is gonna repeat for 8 times. Bending first. The bending part, I think you remember. Just show it a little bit. For the bending part, so we have this one, row number 1, column number 3, row number 2, column number 2, and row number 3, column 2 and 3, which is too many Y's around, which is this one, row number 1, column number 3 times L. So it's a multiple of the node number. So it is the partial derivative. We get the dn dx, and then the next one minus dn dy, and the third row is the minus dn dx and dn dy. Okay, all right, minus dn dx. Is it up? I think hey, we found something, huh? This was supposed to be good that we came across. This was supposed to be the same as this one. Well, to make it easier, I think it should be done this way. We do not have to spend time calculating. It is equal to b mat b 1, 3 times L, right? So this one particularly is the dn dx, but we do not want to calculate. We copy this value from above that was already calculated. Okay, is that so? Or it's already correct? Fine. Anyway, already correct. We still can make it b mat b. This is 2, 3 times L minus 1. Okay, perfect. And then for the shear part, check correctness a little bit. For the shear part, we have the b mat of the first column, okay, 1, and the first column equals to d phi dx. So this comma 1, and then 1, 2, and then dc dx. Actually, this can be taken, right? This can be taken from the. It is actually this one, right? So it is a b mat b 1, 3 times L. I just wonder if this 1, 1, this is not 1, this is L. So the shape function L with respect to 1 is the C, and then the C with X. Let me check the index a little bit. I don't want to come into the jackpot of any kind. Okay, so this one here, we are talking about dc dx. dc dx 1 is the dc dx, or 1 2 is the d eta dx. Okay, so this is correct already. dc dx 1 dc dx 1 2, this is with respect to eta, and this is a shape function, derivative of shape function with respect to eta, so that gets along correctly. Alright, so we can take the d phi dx from this b mat b over there. Right, then the next one is the shape function value itself. So at the column 3L, line 7, okay, let me see. Sivaram has something minus 71. This one, right? Minus, right? Okay, let me go back and see. 71 is the minus at 70, and 71 is the plus. That the plus is already okay, right? Let me switch you to here. So the line 71 is this one, partial derivative of shape function with respect to y, right? You mean this one? And this one is the slide 71 b mat b. Okay, let me see. B mat b. This one is the negative value. Okay, all right. Yeah, I see. Thank you. So it switched. All right. Yeah, good. Thank you. So okay, I put the minus sign to cancel out with the minus over here. Thank you. Okay. Now I come back to here. This is shape function L, 1. Okay, it has just one. So this is the shape function. Only the shape function. And the next line is the derivative with respect to y. So if it is the derivative with respect to y, just that, it has to be the same as this one, dn dy. Copy and put it here, dn dy. And last one is the n shape. Okay, right column now, minus n shape L, 1, which is okay, which is correct. So this is a minus n. N dn dy, minus n dn dy, n and partial derivative with x. Okay, right, so looks good now. And we then move forward to here, the assembly of the the integration points. We assemble everything. So k ili, which was resetted over there, k ili equals to k ili itself, b mat b bending transpose d mat b, b mat b Jacobian of transformations, and the weight of that point of the j and weight of the k, plus the b mat shear d mat s, which is just a scalar, and b mat s Jacobian of transformation, the weight. Okay, that looks good. Okay, we finish it up. So we finish the loop over the integration point, and then the plugging in. This is the part that we stop. So let's take a look at this thing here. So I'm gonna cases. Where is the cases? Cases is a 3. Okay, looks good. So it's correct. Just copy it first and paste it. So the in each cell we have 3 by 3. So let's start from changing this to 3 to 3 to 3 and to 3. Okay, this has to be 3 and this also has to be 3. and copy this and paste it. Okay, so has to start with 3 minus 2, 3 minus 2. And then we're gonna have the 3 minus 2 minus 1 minus 2 minus 1. Okay, that's gonna be a lot of. So we fix this first. We're gonna have the same. Okay, same minus 2, same row first, minus 2 and minus 2. Okay, and the last one is going to be last one is going to be minus. We can do it this way, minus 0. So the format is just alike. Minus 3, 2, 1, minus 2, 2, 2, minus 2, 2, 2, 1, 0, minus 2, 2, 2. Okay, beautiful. 2, 2, 1, 1, 0, 0, 2, 1, 0, 2, 2, 2, 2, 2, 2. And there it is. We copy the whole thing and we paste it there. Now we don't change the second index. We're gonna change just the first one. So it turns out to be just 1, 1, 1, and 1, and 1, and 1. Okay, minus 1, 1, 1, 1, 1, 1, 1. Okay, this and this. So 1, 1, 1, 2, 2, 2, 1, 1, 1, 2, 1, 0, 2, 1, 0. Looks good. 2, 1, 0, 2, 1, 0, 2. Okay, 1, 0, 2, 1, 0. So we don't change this. 1, 1, 1, 1, 1, 1. Okay. So first index is changed. Second index does not need to be changed. This does not need to be changed, and this is changed. Next one. Then I erase this. So 1 turns out to be 0, 0, 0, 0, 0, 0, and 0, 0, and 0. Okay. What else? 2, 2, my 1, 1, 1, 0, 0. This does not need to be changed. This does not need to be changed. So just this change. Okay, looks perfect. I just break the okay, break them into the sets like this. Now the plugging in is perfect, so we are ready to move forward to the next step, the construction of F6. We have the enforce. Okay, so that was taken. F6 equals to, actually this code in the past, it has to be like this, equals to, oh no, we make F6 for the degree of freedom already, so it does not need to be superimposed, but it doesn't hurt to make it this way to make sure that if it needs to be superimposed, it's not going to replace the value. So here is equals to F6 equals to F6 itself. At that point, add up with the part you obtain from the input file. And next we enforce the boundary condition. Boundary condition is enforced. So BC, okay, all this we can reuse the old code. I to this, F6, okay, it's also enforced, perfect. And then we solve the matrix, we inverse. Still this part told you it could be improved to the better solver. If you're using MATLAB, actually it is sort of easier and it has better solver. Now insertion of the restraint back into the place. Okay, so this is just for the purpose that we want to plot the thing out. Alright, wait a minute, let me check. So insert back. Okay. Alright, I just wonder what I did at that time. It looks so amazing. Okay, so up to this point here, I think it is perfect. It is good. We can do the first plot. So what I did, I never memorized things, so I forgot all the figure thing. Okay, fig. All right, fig. Then deform shape plot first. Deflected shape plot. So we start with the deflected shape for the first. Oh, copy. We need to plot it out. The thing below, we will need to do the recovery, of course, but not right now. We can get to see how the thing looks like. So displacement, displacement at the point. Okay, I remember this. So I checked this before the class already. We can plot. The point is that we have several commands for the plot, and the 3D plots, you can do the plot and 3. And plot 3 is going to take the data structure, which is like x, maybe y in vertical, x in horizontal, and let me do it this way. So this is going to be the data structure for y, this is the data structure for x, and this is going to be the data structure for the z. Z is the w for our case. So we have the z value, but it is not in this form. It is in the vector form. Okay, so it is the headed for us to change from the vector into the matrix data like this. For example, if you have like 1, 2, 3, okay, so you go like this, and this is also 1, 2, 3, and you go like that to the right, and then things in here, I can make it like equals to random number. Okay, just something like this, and we can play with this. So this is supposed to be the y, equals to okay, and x is going to be this one. Still sleepy somehow. No. X is supposed to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have x, we have y, and then we have the z equals to. Just come back to Excel and copy the random number. Well, that's gonna make like a ugly profile. Oh, syntax error. What is that? Syntax error. Up. Can I do it again? If it doesn't work, then you gotta put it in the, not good. You gotta put it in the code. But the thing is that I was trying to illustrate you that the command plot 3 like that is going to use the data structure, which is like x, y, and z. So the x has to be this, right? Y has to be this, and z is going to be this. So it's gonna perform the plot, surface plot in the grid-like pattern. But the point is that here we do not have z in this one, so we're gonna take like quite a lot of quite some time to code and to stitch it back into this shape, which is actually possible because each of these we have the xy core. You can convert everything back into here, but I do not want to get into that. So we're gonna look at this. Actually, for this you can just copy and try to execute. Yeah, and that's it. This is what we have from this piece of code. So it does the mesh generation or the grid generation from the scatter data we had, and okay, grid was made and surface plot was carried out. So we are going to do the thing like this. So you come back to the editor, and then I paste that thing here. I am not going to use it, but I just want to have want to see the framework of it. Well, of course the x and y will be matching, okay, in dimension. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And likewise for this one, z is also 10. Okay, so yeah, let's use the figure 1. I'll put a and this clean stem, I don't need it. Grid on, that is not necessary. We need to discretize the x and the y. So x tick, okay, and y, generally it should be tick. I need to maintain it like this. X tick and y tick, and the command line space is going to discretize the x, min Where do we get the x? X come from xy core. Xy core where? Whichever row, but this one, right? Column number 1 is the x coordinate. And then for our purpose, okay, this is the max, xy core, same. And now it is the matter of fact, how many discretization you need, the more the costlier. Make it 100. Should be enough for us. And likewise, comma 2. And then we need a new xy, right? xplt, x and y for plot equals to mesh grid. Well, quite a good piece of code. X is the original x, okay, which is the xy core of this one, and y is the original y. Okay, sorry, not here. Let me cut it out here. It's gonna need the mesh grid is gonna need x tik and y tik, okay, and the z. So I make it z plt. Z plot is coming from the grid data. This grid data does sort of interpolation because it obtains the x and y and z from the number from the points that you have. It might not be the grid data, and then it computes the z according to the capital X and capital Y, right? So it's a sort of, let me use this to explain. I'll copy this one again. I just want to explain what's going on. Okay, and let's just make it. So this is from the example. You have the data point like this, scattering. It is not in the mesh, in the grid type, in the grid-like style. And in order to plot in here, this is the grid data. And to make from this point to that point there, we were doing, okay, first the x, y, z, which are which constitute of this, okay, obtained. And the x for our case is the xy core first column. This is xy core second column, and this is the DISP, which is the displacement vector, and the number of z is equal to the number of nodes. Likewise, number of x and number of y are equal to the number of nodes. So the stem tree is to create this plot, okay, and okay, grid on whatsoever x, v, y, v. It does the discretization. So in one direction we get the max, we get the min, we get the max. This is the min, this is the max. So the between the min and max, it is discretized into for this it is 20. And likewise for another axis, okay, you find the max, you find the min, maybe somewhere around here, and then discretize into 20. And then x and y, which is going to come as grid coordinates, right? Come from mesh grid, the x, v, y, v for this. And for the z, you take the z from the original x, y, z, okay? and from original x, y, z you have this data, and the code here, the grid data, is going to do the interpolation of the point which is in between all these nodes, such that it is possible for us to construct this surface, because otherwise you have just a node, so you might get just the line, but you don't get the surface. Or you might get the dot, but you don't really get the surface plot out like this. So the x, y, z come from above, and then we find the z value at the x and y, which is on the surface, on the grid there. Okay, so and then finally the function surf, which is surface of x, y, and cap x, cap y, cap z, is used to plot this one here, and then the shading is interpolated, right? So just that. So for our case, we're gonna do the same thing. Where is it? Z plot is equal to grid data of so we have x, y we mesh grid already, and then Z is a grid data, x, y yes it is. I should take this one because I made it for paste it, and this, right, displacement vector, it looks like this. So the dimension match with the xy code, because we did the back insertion in here, so the size of the ISP is gonna come back to original, like number of xy code. It matched with the number of nodes, in other words. And we have the x PLT and y PLT, and that's it. So we get the Z plot, and now surface of the x plot, y plot, and z plot. That's it. Axis equal shading, interpolate. Okay, and erase this and return. I do not execute the part below yet, because there's gonna be a lot of things to do. We will obtain the previously when we work on the plane problem, we get strain, we get stress, but now in the plate bending, we're gonna get the moment per unit length. So mx, my is gonna be calculated using the stress recovery routine like this. But for here, okay, I think it is good enough, and we will construct a problem for us, maybe just the simple plate bending, and we'll see. We need to use the rect match. So we go up, and here option, we start from option 1 first. We need to put the boundary condition element type, make it 4, quick, nx make it 20, ny 20, hx1, hy1, file name, plate 1.text is just that, and okay, which one? Oh, sorry, I should have Control C. Okay, I execute, and I should. Okay, I close everything down already. I just re-execute. It's gonna take some time again to get the node number for some reason. Okay, almost. Okay, done. This is our domain. I will look into the plate one. Plate one is not updated yet, so we come back here and call rec mesh but 2. We do not need to close the we do not need to close this speaker. We will need it. So the element type is for the info. I can put it a bit. Why? This is what for the class number 26 of April 13, 2020. Just like this. So we come back later. We know plate thickness. Since the dimension is the size is 20 by 20, I think because each element is 1, right? So this is 20 by 20. I think maybe 1.0 is okay, not bad. Number of nodes, number of elements, and this a whole bunch of XY coordinates is given here. Nmap is given over here. Okay, we need element property. We need the number of integration points to reduce integration. No. Number of essential boundary condition. We come back to it later. List of restraint DOF. We'll just do the Excel here. We're gonna need the Excel for, well, forget it. We have in total 400 elements. Oh wow, 400 elements is there. Yeah, prepared. Check it a little bit. What is the input we need from? We just need the XY coordinate, right? Sorry, I increased the size. Plate thickness, XY coordinate, nodal point mapping, element properties, and okay, we will not get more than that. So elastic modulus and Poisson ratio must be the case, and elastic modulus 100, Poisson ratio 0.2. Copy that. Okay. That's it. Copy and paste in editor. eprop paste, and that's it. Yeah, 400 is gonna be a while. Okay, element property is there. Essential boundary condition. Well, take a look at it. Essential boundary condition. It depends on what you want. I think the essential boundary condition can be like this. Maybe we start from the one. Let's make it like a one-way slab. So this, which side is going to be easier? Yeah, this side and this side are going to be enforced as a essential boundary condition. We can fix the displacement or the deflection. We can fix the rotation, but we make it like a simply supported beam, one-way slab, right? So the rotation will not be restrained. I'm gonna fix only just the vertical deflection. 1, the DOF 1. 2, DOF will be 2 multiplied by 3 minus 1, which is 5. Number 3, 3 multiplied by 3, you get 9. Sorry, minus 2. So 1, 4, and then 7, and so on. So we have node number 1 to node number 21. Come back here. Node number 1 to 21. Okay, need 21. And then we're gonna make it this way, just 3 multiplied by this and minus 2. That's it. And you have another row which is on the top, 421 to 441. 421 to 441, 421 and 422 all the way to 441, and that's it. Then we get the number of we get the essential boundary condition. I think I sleep well last night already. It's not good enough. Let's take a look at the count. It is the total number is 42. So we come back to the editor. Maybe make a copy first. Copy and oops, not just copy. All of these are going to be 0 because we will just force it to 0. Come back. No, actually this one we didn't use the Lagrange multiplier, so, and this is the wrong place. We were not supposed to be here. It's supposed to be here, and we have 42 numbers. Number of force boundary conditions. What should that be? The force boundary condition. Okay, so let's take a look. The force boundary condition, we can apply the force throughout, but the point on the edge like this is going to be just a half of this point. Because the tributary area is less. We can apply the pressure, but that's gonna need the code for the pressure integration in order to come up with the force vector. It's gonna be a sloppy one. Okay, let's make it. The point, the node number is going to go up to 441. So 1, 2, and that's gonna go to 441. 440. Oh, too much. 441. And then make it 4. Enter. Let's take a look. Well, this is totally manual. First of all, we look at these following nodes. These are having just a quarter tributary area. Well, we should make the code for the force vector calculation, but I just want to run and test this code. So well, manual first. First of all, these are not the degree of freedom yet. Insert. We need the degree of freedom, so this is going to be this multiplied by 3 minus 2. Okay, in order to get the degree of freedom, we get the degree of freedom. Now the node number 1, node number 21, 421 and 441 are gonna have only just a quarter, which is 1. 121, 421, 1, so you get 1, 21, you get 1, 421, you get 1, and the 441 you get only 1. Okay, that's it. And what else? The line here, 2 to 20, you get 2 because tributary area is a half of the node in the center, like that. So it turns out to be 2 from 2 to 20. 2 to 20, and get 2. What else? Not only that, 422 to 440. Just do the easy tax first. 422 to 440, you get the 2 drop in. And what else? 2243, the increment is every 21, right? 21. So come back to this point here. Increment is 21. So let's do it. Is it the mod or div? Oh yeah, I need the comma 21. Whoop. So the 22, yeah, okay. And the 22 is here, then the 43 was supposed to be 0. So we look at the 0. 0 is 22, and this is going to be just 2, right? This is the edge, so it has only 2. It's not having 4. 2, and then look for the next 0. Next 0 is 43. Is it so? Yes, 43. So I'm gonna just change like this. Go to 0 again. 2. 0 again. 2. Why? 0 again. 2. Yeah, this is so manual. Maybe writing a piece of code could make it faster, much faster. $295. $295, this one. Okay, way to go. Should be okay. Now it is coming back to that corner. All right. We are done with this side. We need this side as well. So 21. Perfect. 21. Basically it is the node before 22, node before 43. So we just drop in before that 0 number. Okay, come back. Like this, it is 1 already. For that one, we took care of it. And here 2. So 2, 2, 2, 2, 2, 2, not this one, 2. Oh, a bunch of number. Oh, we dropped the we missed the drop there. Okay, it's wrong place. Okay, good that we come back. And what, 420? Let me see, 420. 420, yes, it's supposed to be. Okay. Now these two the column, the degree of freedom and the magnitude of the load to apply. So come back to editor. Number of false boundary condition, forget about it, I put it in first, this one in first. Okay, here. Okay, and number of false boundary, then we can count it from this. How many rows? Why did it give me? Did it? So it doesn't tell count average select cell, count number of selected cells that contain the data. So 441. Seriously? Is it true? Wait. Oh yes, 441. Okay, yes. That is equal to the number of nodes, 441. So okay, we get it. Met boundary conditions, restraint degree freedom is met, integration, everything is met. Okay, save it, and we gonna call this, and we want to change the name a little bit, Mindlin plate, but the file name is the main update. Plate1.text. Okay, yeah, got to change the name of the file. So Mindlin plate is going to copy. Okay, box at the very beginning. What? Plate thickness 400 now. Something. Input read. What is that? Element type is 4. Number of element is supposed to be 400, right? Number of element type 4. Total number of nodes is not given. What? Why is it shifting or something? Element type is 4. Element type is done already. Plate thickness. Plate thickness, I move it to here, right? Okay. So after the element type, is that so? plate thickness first, and then plate thickness, and then number of nodes, okay, and then number of elements, okay. I think he's happy now. Plate thickness, number of elements 400. What is going on? Input read at line 66. Okay. Nodes, number of nodes, number of elements, number of node, number of element, and xy coordinate. So let me see. Let's xy coordinate. So we're supposed to work, right? $66 used to be this what restraint degree of freedom. Okay. Then I don't need to call it. Just okay. Save it like this and input read. And the file name is plate1.txt. NELE element type. Why does it show like this? Okay, element type this, and NDE. Okay, I like it to show NELE. It shows off. And then the problem is at 66.5. BCDF equals to dummy. So let me get off this listed off. Okay, now let's see. NELE 400 correct, integration point correct, reverse integration, NBCN 42, and something is wrong. 42, we were supposed to have element property is good. 42, let's see how many rows. We take the 1304 minus 1262. This is 42. It's correct already. So what is the error? Non-conformant argument at the line 66. 66 non-conformant. BC I comma 1 equals to dummy. Oh, okay. So we do not need the 0. Because it is because it is enforced by the row column elimination. Okay, got it. Call it again. See if anything comes up further. Okay, it runs all the way to the completion of the piece of code. So then let's see if we check every single thing. Okay, now window BC is supposed to have only one column. Yes. Okay, too late. I just see this too late. Plate 1 dot text. So this looks okay. It's just very long. NINT, everything. Yeah, looks good. Fine. Looks good. Okay, now back to here. Okay, it works. Then we can call the what routine name? The Mindlin plate, and file name. plate 1.txt. It is solving. And displacement, what error? But displacement has size. Call from line 127. 127. What is wrong? Insertion. Okay, now I got it. There must be something like the 2 or so. Here it is. The 2 minus, right? It has to be 3, huh? Yeah. Something left over from the code we had before. Says do it again. Solving. Getting something done. Okay. Oh. Okay. Grid data XYZ must be vectors of the same length. Okay. 136. We'll just keep fixing it. Alright. Let's first see this. Size of XY core and size of this displacement like that. I see. Okay. The displacement we have over here is it includes the vertical deflections and also the rotations, whereas which is actually 3 times of the number of the node. XY core is equal to NNDE in the row number and 2 in the column number. But for DISP, it has the 3 times NNDE, 1. So the size does not match. Okay, doesn't really need to. But we can just call it to check if the final size is supposed to be. It should match with what I just said. So I'll be waiting. Yeah, 441 by 2. If you take 441 multiply by 3 at 1323. Okay, so this is perfect. Yeah, it is just 3 times of the number you have here, and it will not calculate that. So clean it. I will need to transfer maybe the 1 second. Okay, we need it here, right? Transfer vertical deflection. Transfer vertical deflection from DISP. So it's not that difficult. For I equals to 1 to NNDE, we're gonna need to assign W equals to zeros NNDE, comma 1. W I, comma 1 is equals to displacement internet. Okay, it is coming back. 3 times I minus 2, comma 1. 3 times I minus 2, so node number 1 you get DOF 1, node number 2 you get DOF 4, node number 3 you get DOF 7, and 10, and so on and so forth, and 4. Okay, now the W is what we need, and I erase this, and it is not this, but it's gonna be replaced by the W. Hopefully it's gonna work out. Save and call solving. It's trying to plot. What is it? Okay. The axis equal thing, there's nothing wrong. There's nothing wrong with that. The axis is equal, and the value we obtain from the how to do it. Axis, maybe auto scale. Is it? No. Well, it is actually working, but set limit. How do I got to remove the axis equal, probably. Then we get to see the better visualization. Let's see. I just need to adjust the plot, but okay, there it is. Okay, it looks curvy a little bit. The load I apply is positive, so it pushes the plate upward like this, and the reason why it is curvy like this, yeah, the stiffness at the edge is less than the stiffness at the middle part, probably, so it is not going like the one-way slab that we anticipate. It is just a bit okay, not bad. So you can check it with the manual calculation. Of course, you can check the if we use the manual calculation and approximation of the solution by the beam, and like using the Euler beam theory, then put in all parameters, you might be able to get to this. Let's see maybe I just change the problem, the format of the problem a little bit. So we make it the plate with the 4 sides restrained. Okay, and in the editor we have this one. I will do the file save as and make it plate 2. Okay, save. So I'm gonna increase the number of the boundary condition. It used to be 42. Okay, I think you are happy with this already. Then I close it. I gonna call the rect match in order to see the number of the degree of freedom. 1 element type is 4 and x is 1 and y, and x 20 and y is 20, hx is 1, hy is 1, file name is I just don't want, if it writes something, it wouldn't supposed to, because comma what the option plot option 1 will not make the program rewrite anything into the input file, but just to make sure. Previously we input we keep the boundary condition on this side, right? So I'm gonna put more in. So I'm gonna put this side and this side, then it will be the plates that is supported by 4 sides. So this side is 22 plus 21, so go all the way like this. 22 plus, where is the boundary condition? Okay, boundary condition is here. So I have 22, and then this is the 22 plus 21, 43 till 400. Oops. Oh no, it's go like this. 400, just 400. This one, because this one is already restrained before. And 42 to 420. 42 and 42. 42 to 420. Here you go. And then this will be just this. Okay, so I can count how many we have, how many DOF we have. We have in total right now 80. Okay, 80. I just copy. Actually, if I will be kind, I should sort it up, but in the code I embed the sorting already. So plate 2, right? List of the degree of freedom, put it here, and we have 80 numbers, 80, save it, and then we can call it again. So we're gonna call Mindlin plate, and then it is the plate 2. Enter. I should disable this plotting out, solving, and there you go. Here it is. I think you like it. Okay, you can see the boundary condition that all 4 sides, it doesn't move. You can change the color mapping if you want. 0 to 20, 0 to 20, and this is the magnitude. Yeah, quite fun. Yeah. I think we can plot the contour. MATLAB contour plot. Contour XYZ. Oh, we'll see. Just contour XYZ and XYZ. Yeah, XYZ. We have all of them already. Then we can make a contour. Mindlin over here. We did a surface plot already. Then we got a contour XYZ. It's supposed to be this. Just that. And I don't want to see the input read anymore. So element type, I don't care. Well, we can play next the higher order element in a bit. In RNT, just close it all. Why did it show the okay? We're supposed to close like this. That's it. Try. Solving. So it replaced. Is it possible? Not good. Is it possible to contour plot MATLAB on surface? Yeah, I need this. Surf C. Okay, why don't we try it? Surf C. Oh, where is Surf C? Try this one. Actually, it should be like hold on, just in case. We finished this ahead of time. Yeah, got it. Beautiful. So it's not a contour. It is a surface. Oh, the contour is down there, but the contour is not on the surface. So basically, this thing is not needed. If it is surf to surf C, that's it. All contour is the old contour. Well, I'm not satisfied. It is not this. Find 2D field contour. Okay, the contour line is just below. Yeah, this is possible. This looks better, right? It's just a surface. And we change the color map a little bit. Color map jet, not here. Cut it and paste it here. Save it. I'll call it again. Finally, yes, it is. Okay. So here. Right. And yeah, the contour line is just below, like this. Okay. Hope you have a lot of fun to see this color plot of the surface in 3D. And what you need is just the ability to be able to Google and find things on the internet. That's it. I never memorize things, and you can see that I just look up for the things, and I clean it out just right away when I walk out of this virtual classroom or online classroom, and I erase, I dump all this memory, because there is no point to keep it in my brain. I change the program to another, then I got to Google up for it anyway. So it is like just the syntax. It is like a language. So we are ahead of time. We are ahead of the schedule, like about 30 minutes. But I think we shall not proceed any further. The code here is well developed. It could be used for many situations. Basically, the plate bending code. Actually, we can move forward. We still have something to do with the code. We will not just finish up over here. Here. Seems like we are about to finish, right? But and one more thing. I just want to see the mesh. So I put the color map like this. Okay, so probably I'm gonna see the mesh. We still have the part for the moment calculation. So it doesn't show that. Okay, fine. So back to the calculation of the moment. Here we have this thing for the strain calculation in the plane problem, and I put the return over here in order to just stop, because we are not coming across that part yet. Now we are going to continue, but it is not going to be the stress and strain recovery routine. We're gonna get it could be curvature and moment, and make it moment. Knowing curvature, it does not help, because we don't get the sense of the magnitude of curvature, of course. Least square smoothing, well, it could be done. So let's take a look at all of this. Maybe I should switch you to the iPad a little bit. And there it is. When I switch you back here, you can see moment. Where is it? You can actually come up with a shear. So here's the moment. So this moment, moment is this part here. You have the mx, my, mxy. These moments are going to be used for your design. For example, if you design the flat plate, you analyze first in order to get the moment. So the mx, my and mxy are the moment per unit length. Okay, and having this, you'll be able to design the cross section. So how thick it should be, and how much reinforcement there should be in a given cross section. So the moment is this part, the rigidity matrix multiplied by this this part here, which is actually the curvature, derivative of rotation with respect to the dimensions. So these are the curvature, and in order to get this curvature, you come back to the B matrix and then you multiply by the displacement, but it is the element displacement vector. So once you get this, multiply by the rigidity matrix and you are all set. So you have it, you'll be able to plot, then visualize all of this just like the deflection. So we come back to here, moment recovery and moment least square smoothing. Do you feel like smarter doing a lot of things in this course? Plotting out moment. We are going to have 5 quantities. I think you do not want to see the shear strain and curvature. In here we are going to see only just, oops, sorry, is that okay? Yeah, we want to see just the moment distribution and the shear distribution. So for the moment distribution, I call it this way. I will not change the name that we set up for the plane problem, but we need to just change the description. So moment moment XX, moment YY, moment XY, and then shear X and shear Y. Let's make it, yeah, okay. So we are here in ELE DMAT, EMOD, Poisson ratio. Okay, we gotta copy things from above. So let's go up and pick. Yeah, I am lazy to repeat all of this, and it has to be coming down. Element XYZ, I think it is there already. Let's move all of these things down, which is supposed to be here. We have 2 kinds of EMAT. Clean it up. EMOD from E properties, Poisson ratio, dummy, EMAT, DMAT S, DMAT B. It is calculated for each individual elements and we end up with DMAT B. Alright, so clean it up, clean this up. E this, we're gonna need it. The E this is going to be changed, and the E this is going to be 3 times. Element displacement solution, which has to be 3 times the number of nodes. So it is good now. John asked me something for a homework. Do we need to number 6? Okay, well, let's talk about that later. Do we need to number 6? Which is the beam? Well, let's come back to this later. If you can explain clearly, that will be better. I don't get what number 6 you mean, John. Come back here, element X, Y, and we migrate the value here. Loop over the Gauss point. We are not going to use this. Okay. We're gonna need it. We're gonna need just to here. K element. Why do we need a K element? Oh, yeah, that is for the smoothing probably. Deform shape plot is not necessary here, right? Well. Okay, so FVLE, first of all, just know that this is gonna be MXX, MYY, MXY, sigma, it is the shear, and this is the shear in the Y side. Okay, and then KELE equals to element type. Okay, this is for moment smoothing, moment and shear smoothing. And then number of integration point, okay, and shape is called the B matrix. Now it's going to be adopted from before, but B mat, okay, this part will be taken from above. Let me just space it out. Go back up to copy. Let me just take this. C eta, they have it already. IK, JK, dndx, we have it already. And shape, it was called already. Then this, okay, B mat B and B mat S came in, and then the B mat B was calculated. B mat S is calculated. The KELE is not going to be the requirement, right? We're gonna use the moment is equal to B mat B times EDIS. Do we have EDIS? Okay, now EDIS is not quite correct, because the EDIS was supposed to be 3 minus 2 and 3 minus 2 here. This is the W, which is the deflection. Okay, and then the next line is the theta. So minus 1 theta x, and last one theta y. V and okay, so EXYC is XY core. Okay, this will not change, but EDIS was changed to 3 already, but I didn't change in here. Lucky that, okay, it was caught before. EDIS, well, so it used to be EDIS, EDIS, moment, I don't, and then multiply by the D mat B in order to get the moment, right? D mat B, bending rigidity matrix multiplied by B matrix of the bending multiplied by the EDIS, and then shear is equals to D mat S multiplied by B mat S multiplied by EDIS. That's it. So these lines are not necessary. And okay, clean it out because this is from the one before. E strain, okay, clean it out. I figure out I just need to, okay, now numerical integration of what? Plugging in element vector, the matrix into, okay. Don't remember what is this. K inverse, K this. What is this? The K inverse for what? What is this to be used below? Do not delete this. Okay. Yeah, that's a lot of things after. So I'll clean this E stress, E strain, F E L E, and shape moment MMNT 11 MMNT and this will be SHR and SSHR, and we don't have this one. Okay, looks good. So I will clean all of this. Numerical integration of this FELE1 equals to, and then I got to look into element type. Okay, just FELE1 shape, M integration, M moment, Jacobian weight, blah blah blah, and the KELE. This will not be changed. It is for the least square smoothing. Okay. Plugging in element type, okay, up to the 6. We don't have more than that. And cases is equals to the thing down here. Okay. I think we don't have anything to fix it. We can use it. Deform shape plot. We don't need this. Because we just plot here moment plotting option. Wait a minute. Color plotting. I just wonder where is the least square plugging into the vector. Okay, numerical integration was done, and then F6 is plugged in, the K6 is constructed. KINV, let me find. Where? Oh, okay, yeah, so it is here. Then name it PE. Why? Control Y PEXXX PMXX. Okay, PEYY turns out to be PMYY. PEXY in order to and then PMXY. PEXY is not available. PGXY. Okay. PG. Okay, and what? PSXX. It is there. Okay. Only just the PTXY is not PTXY. PTXY. We need to remove this part of the code here, and well, okay, this part here. Okay, PTXY, we don't have it. Fine, next PTXY, I erase it. Fine, next PTXY. Fine, next PTXY. PTXY. Fine, next PTXY. Fine, next. It doesn't find anymore. Okay, good. Yes. I think it is quite ready. Hopefully, I don't want to bump into the bug at the end of the class, but we will get everything done completely. So moment is going to be plotted out in figure 11. Okay, and Q4. Fine. Save it and see if we get everything we want. First thing. Okay, the other things are plotting. Boy, slow. Okay. I cannot find the fifth figure. Where is it? Okay. Moment XY, shear and shear. Looks good. So there is nothing better than having the code fixed, no bug, plots out nicely, and that's gonna make the day. Almost done. And you can use this for the design of any slab. The thing is that you need to get the match. And there it is. Beautiful. So I can wrap up this class. The code will be shared on the Google Drive. And do we need to number 6? Okay, someone, sir, I think John means that do we need to do the number 6 of the super assignment, because most of us are not sure in your instruction. Okay, let me revisit that to that point, and then I will put the clear instruction, and I'll give you instruction for that in a bit. Okay, for now, just leave it. Okay, so you might not be able to submit on time. I think the deadline is on the 15th. So let me look into that point. And just for now, you might not submit that number 6 on the 15th. Okay, if the instruction is not clear. Okay, and I will look into it and see, okay, what is not clear, and we'll let you know if it needs to be submit or not. Okay, all right, but for now, I'm gonna wrap up this class, and I will upload this class video very soon in this, maybe evening. Okay, so please please play with the code, and hope that you will find it useful. Okay, have a good day. Bye bye.